Thanks for the introduction, Florence. Thanks for the invite also. It's great to be here. So indeed, my talk is going to be a little bit, at least there's going to be some common ingredients with the talk of Francis this morning, and okay, a little bit also with the previous talk, at least in the motivations around privacy. Right, so let me just go dive in. So this is joint work with a bunch of people at Inria, also at EPFL and at University of Saint-Etienne, and sort of browsing a few papers. And I'll try to start with some context and motivation. So the context that you can think about here for sort of motivating what I'm going to present is sort of this data that is collected at the user end. Okay, so nowadays there is sort of those connected devices that are becoming widespread. Of course, or mobile phones, but also these home assistants, smartwatches, and so on. And these devices, they are collecting increasingly sensitive and personal data because they are closer than ever to the user. So you can think of browsing logs, some health data, some speech data, some geolocation, and so on. Okay, and so there's sort of like a little bit conflicting goals here. On one end, it's a great opportunity to provide more personalized services to users. So, okay, there can be a benefit in that, but on the other hand, that means users have to give away more and more personal information in exchange for those services. Okay, so this is perhaps illustrated in sort of like these two mainstream strategies of sort of trying to leverage this data to learn interesting models for users. The first one is the centralize scenario, okay, which is the classic thing. In the centralized scenario, you're going to ask users to give their data and put that on a big server. And then you have, okay, you can learn the models there, okay, on the cloud or on a sort of big server. Okay, so this is what most of the industry, for example, is currently doing. So this is good from the point of view of utility, because then we can learn models and we have direct access to data, sort of unlimited access. On the other hand, for the users, it might not be so good, at least from the perspective of allowing users to have control on what data about them is used or is collected. Sometimes it's not very clear for users what is being collected and what is the purpose. So there are issues of privacy and sort of security. This central database can be attacked. Okay, we have seen a lot of leaks in the recent years at Yahoo, for instance, and many other companies. And then also from the service provider point of view, it's also like a very big infrastructure, okay, that this company, for instance, has to maintain. Okay, so this is one approach, a very common one. The other one, which is sort of the other end of the trade-off, is to not share anything with anybody, okay, and learn only on device. Okay, so there has been also actually some companies that have promoted this approach. In this case, it's in a way best for privacy because users do not share any data at all. But of course, it's bad for utility. Okay, so for many users, they just have their local data, which is typically not much, and so you cannot learn that much interesting things on isolated users. Okay, the power of this data usually comes from sort of cross-analyzing many people. Okay, so the goal of this talk at the high level is to try to find a sweet spot between these two extremes. So we want a way where we can learn something useful, but without giving away everything about our sensitive data. Maybe revealing a bit of information, but not too much. Okay, so we can sort of have maybe a better trade-off than either of these two. All right, so there's been some related work a bit at least in machine learning recently. So you might have heard of federated learning, for instance, which is some framework that is promoted by Google. So they have started to deploy this a bit for like the Gboard, okay, trying to predict, for example, next word that people type on their smartphone. And the idea is that, okay, we're not going to centralize the data anymore. Maybe we're going to try to keep it on each user device. And instead, we're going to sort of learn in a distributed way. Okay, so federated learning is sort of like maybe a little bit rebranding of what we already know as sort of distributed machine learning in a way. So the idea is that there's going to be a central server, a coordinator. This server is not going to ask for the data this time. It's just going to sort of initialize a model that is then shipped to the user devices. Okay, the user devices are going to do an update, compute an update based on their data, maybe like based on a gradient descent algorithm, and then send back update, and then the server will aggregate these updates, make a new model, and so on. Okay, so it's kind of like distributed way of training the model, where now the users are not sharing their data anymore, but they're sharing updates computed on their data. Okay, from the perspective of having fast algorithm, this is sort of centralized in the sense that we still have a central server, so there is a heavy dependence on that. So this sort of reminder of Francis' talk where he was sort of showing some kind of centralized approach, which, okay, this guy is a single point of failure, and if you have many users, like in the millions or whatever, this becomes like a very big bottleneck, this server. Okay, so what we're going to be interested about in this talk is sort of more fully decentralized learning, which is this learning in a graph thing. Okay, we don't have any master anymore, and essentially the devices, they exchange by some peer-to-peer asynchronous kind of message passing along a communication graph. Okay, where here an edge between two devices, okay, tell you that they can exchange messages, and still everybody keeps his data, and you can design algorithms that look a little bit like the previous one, okay, where devices locally make updates to models, and then they share with their neighborhood. Okay, so this avoids this single point of failure problem, and typically this scales very nicely with the number of devices. Okay, so we're going to be sort of working in that framework. Oops, but okay, trying to make a slightly different feel, and one of the main differences is going to be about personalization. So unlike what Francis presented, we're not going to necessarily try to find the same model for everybody, some kind of consensus model, but we're going to want to learn personalized models for users. For applications where users have very different data, and maybe a single model is not very good fit for everybody, okay, or it requires the model to be very big. Okay, so instead we're going to try to learn models that can be different from a user to the next, but of course we want to collaborate to learn those. We don't want to learn them in isolation. And so to do this, we're going to leverage some similarities between users. Okay, so if we know that maybe some users are similar to each other, then they can maybe share more information to learn something better for everyone. And okay, in the first part of the talk, I'm going to assume that this is given sort of as input, but I'll show at the end, if I have time, that we can learn it, that similarity structure over the user. Okay. So we're going to want to scale to a large number of devices by using fully decentralized learning, and of course, I haven't forgotten the initial, maybe one of the main initial motivations, which is privacy. So we're going to make sure that whatever we exchange with others satisfies some formal privacy guarantees. That is, it doesn't leak too much information about each person's data. Okay, so this is kind of like the target, the menu. Okay, so let's see how to formulate that. So I'll introduce some notations. We're going to have a set of n users. Okay, each user, so user, device, agent, whatever. I'm going to use those maybe interchangeably. Each user has a personal distribution. You can think of a user as sort of having its own data distribution over some feature space X and label space Y. Okay, these we're going to be assuming they are common, so they are the same for everybody. It's more like the distribution of the data that is user specific. So it's like it defines a personal supervised learning task. And then each user has a local data set. So this is couples of like X and Y's, like features and labels, of some size which is specific to that user, MI. Okay, some users might have more data than others. And okay, this local data is drawn from that user distribution. Okay, and the goal of a user is to learn a model, let's say theta I. Okay, so some parameters in a sort of vector of P parameters that generalizes well to its own distribution. Okay, so the goal is really personal. So what can you do if you learn in isolation? Okay, let's assume the user is alone in the world. Okay, what can it do? Well, it can just try to learn on it based on its own data. So here you recognize sort of similar formulation as what also Francis presented this morning. This is the classic sort of empirical risk minimization formulation for machine learning. So if I define a loss function that takes a model and a data point and returns some kind of discrepancy between the prediction and the ground truth labels, one classic strategy is to learn the model parameters that minimizes the average loss over the data set. Okay, maybe I can add some L2 regularization or whatever. Okay, so this is sort of, in a way, like a purely local solution if user only knows about his own data and learns in isolation. Okay, which might not work too nicely. So our goal is to improve, sort of trying to reformulate the goal now a little bit more precisely. We're going to want to improve upon this purely local solution by communicating with other users, but without leaking too much information about SI, the local data. So how are we going to do that? So we need to specify how users can sort of exchange information. Okay. So we're going to be in this decentralized setting. So we're going to use asynchronous time. So this is a way of modeling sort of the algorithm as each user acting independently, okay, waking up at some random times and taking some actions. Okay, so there's no centralized notion of round for everybody, like global clock saying this is round 1, everybody does something, okay, everybody done round 2. Here, this is really each user sort of becoming active and taking some updates asynchronously and in parallel. Okay, so we can still formalize our algorithm by thinking about a single clock with a counter T, which ticks each time if one of the local user wakes up, but we're not going to need that user know this counter. Okay, so this counter is something global that counts how many people I've become active so far, but this doesn't need to be known by the user so that they don't need any synchronization whatsoever. And then the communication model is going to be that we're going to be able to exchange over this, the edges of a graph. And the difference with what Francis presented this morning is that this graph now has some semantic meaning. Okay, it's not just communication constraints saying who can communicate with who. It's a way to restrict the communication to pairs of most similar users, okay, so that they can exchange directly more information. Okay, so it's still going to be a graph, and we're still going to sort of send messages along the edges of a graph, but this time it has a sort of like a semantic meaning, and in particular it's going to be weighted by, so the edge between I and j has weight wij, and this thing reflects the similarity between the learning task of user I and j. Okay, and so for now I'm going to consider that this is known, this is given to me as input. Somebody told me, some oracle told me, okay, here are the sort of similarity relationships between users for this task. And now I'm going to try to leverage this information to learn better models. Okay? So we're going to formulate the problem as some global objective function and then try to optimize it in a decentralized way. Okay? So what is the objective? So we want to find models, one for each user. Okay? So we have models from θ1 to θn. And we want to minimize the cost. Okay? This cost has sort of two terms. The first term, if you ignore for a moment this constants in front of the loss, this is simply the local loss of the user I using its model. Okay, so this is just as before. Each user is trying to have small loss on its own data. And then the other part is, the red part is what enables collaboration. So this is saying, this is a little bit like a soft equality constraint. Okay, instead of having consensus for the models in the network so that everybody learns the same thing, now we bias the models of strongly connected users in the graph to be similar. Okay, so this is how we enable this sharing of information, essentially. And there is a trade-off. So here we have this CI, which is the confidence of agent I. So you can think of this as proportional to the size of its training set. If an agent has a lot of data, it's going to trust more its local loss. And if it doesn't have so much data, it's going to trust more maybe the information coming from neighbors. And then we have this mu parameter, which sort of gives like a global trade-off between the two terms. And this is quite nice in terms of flexibility because you can really interpolate between learning purely in local models. Okay, if I set this to 0, then this formulation just becomes everybody learns in isolation. And if I make this go to infinity, then essentially I'm learning like a shared model for each connected component of the graph. Okay, because this soft constraint becomes like a hard constraint, essentially. Okay? So if my graph is connected and I make mu go to infinity, I recover the consensus approach, learning a single model for everybody. And if my graph has different connected components, then I learn sort of models for each cluster, for each connected component of the graph. Okay, and in the middle, I let everybody have its model, potentially differently from others, but still being influenced by people. Okay, so we can sort of nicely interpolate between the different classic solutions here and get some nice trade-off in the middle. All right, so I hope the setup is clear, and now I'm gonna maybe start by ignoring a bit the privacy constraint and introducing a non-private decentralized algorithm. Okay, let's start simple. Okay, so this is maybe some things that I'm gonna skip. So these are kind of like properties of the objective function that you need to assume to essentially design the optimization algorithm and prove its convergence rate. But those are classic assumptions like smooth gradient, convex or potentially strongly convex objective functions. And then the algorithm looks like this. Okay, so I think it's at least the main idea is very simple to understand. So let's denote the neighborhood of user I by this ni, okay? So those are all the users j with which the user has non-zero weight. Let's start by initializing the models of everybody to whatever. And then at each step t, we know that, okay, we are running the algorithm asynchronously, so there is a random user that wakes up. Let's say it's user I. And this user will do an update of its model by essentially doing a trade-off between two things. It looks like a gradient descent update, but only for the model of that user. And it's a trade-off between improving the local loss, reducing the local loss by essentially taking a step in the opposite side of the gradient of the loss of the local data, and making a convex combination of the models of the neighbors. Okay, so we recover sort of the same structure as in the objective function, where both we want to have small loss locally, but also have a model that looks like sort of convex combination of neighbors. Okay? And then once the user has done this update, it's going to send it to its neighborhood so that they have the information that they need when they themselves wake up. They know the neighbor's model, and so they can make their updates. Okay? And so these updates happen asynchronously and in parallel in the network. If you have a very big network, these things are, okay, sort of activate at different places without any synchronization. Good, so that looks good. We can show some kind of rate, which is not very novel because you can actually recover some kind of coordinate descent algorithm when you do this. So you can show the rate pretty easily. I mean, there's no strong novelty, but it's a fast rate. If you have like a strongly convex function, we have this kind of exponential rate, okay, in expectation. So this is the initial gap of the objective function at the starting point, the optimality gap. This is the expected optimality gap after t iterations, and essentially this gap is reduced by some constant factor. Okay, like shrinks by a constant at each iteration. This thing is smaller than 1, so this makes this, okay, go exponentially fast to 0. Okay, so now what do we have? Essentially, we have an algorithm that optimizes our objective function in a decentralized way, learning models that are potentially different for each user, but with collaboration by exchanging parameters. Okay, so what about the privacy goal? Okay, so what I presented is, okay, in a way not that bad, because at least the agents, they never communicate their data. Okay, in that algorithm, I only communicate model updates based on my local data. But unfortunately, this is known to leak quite a lot of information in many cases. This is quite well documented now. Okay, so even though I'm not sharing the data directly, I'm sharing quantities that are computed from the data. And an adversary that would gather everything that I'm sending and then could potentially reconstruct a lot of information about the dataset SI of the agents. Okay, so if the data is insensitive, we want to be careful with this. We want to make sure that Okay, say it's not enough that I'm not sharing the data directly. I want a stronger guarantee against an adversary that would observe everything that I send. Okay, and then would look at this information and then try to infer things about my data. So the adversary observes what people send, but of course it's not able to observe the internal memory of agents. Okay, so whatever you keep locally, we assume it's secure. It's whatever you send outside can be eavesdropped. Okay, so you can think about the NSA maybe sort of listening to everything that you are sending, which might be the case. And this is the adversary we're trying to protect from. And we assume the NSA, which might not be true also, cannot look into your device. Okay, so we assume sort of security for the devices. Good, and so the goal is to formally guarantee that little information about the local data is leaked by these updates that we are sending. Okay, so we need, of course, a formal definition of that. And the one that we're going to use is sort of now sort of becoming like a gold standard way of defining privacy, at least in such contexts, which is differential privacy. So differential privacy is as follows, okay? So you assume that you have some algorithm or some, here, mechanism M. Okay, this thing takes as input some data and then spits an output. Okay. We say that this M is epsilon delta differentially private is if for all couples of data set S prime that differ in a single data point, so they are the same up to one point, and for all possible outputs of the mechanism, then essentially the probability that I see a given output when I use S as input is pretty much the same as if I had given S prime to the mechanism, okay? And almost the same being quantified by these two parameters, epsilon and delta. Okay, so you have sort of like a bound on the ratio of probabilities. Okay, and this has to stand for all SS prime that differ on a single point and all possible outputs. Okay, so why is this intuitively a good notion of privacy is that it sort of guarantees that the output of the mechanism is almost the same regardless of whether a particular data point was used or not. Okay, so it's kind of like thinking about posterior in two possible worlds, one world where your data was used and another world where your data wasn't used. Then in these two worlds, the output, the probability distribution of the output should be the same, or close enough. Okay, so this is what it's saying. So this is really sort of like an information theoretic notion. Okay, there's no computational assumption on the adversary, like maybe the adversary cannot solve NP-hard problems or whatever. There's no assumption like that. It's really about the information contained in the output in a probabilistic sense. Okay? It has very nice properties that I'm not going to really spend too much time explaining now, but it is robust to some background knowledge. So there was a question before, maybe which was related to this. So differential privacy is nice in that way because essentially it bounds the gain of the gain of information that you get from seeing the output about a particular data point. So, okay, maybe you knew a lot about that data point before, but okay, it's still a meaningful definition, and it doesn't make a lot of assumptions about how the data is generated or the prior that the adversary may have on the data. And it is also a very convenient definition to work with, and one of the nice properties that it has is composition. So if I run several differential privacy mechanisms on the same data, then the combined output is also differentially private. Okay, so this is the simplest case, simplest result. If you have two epsilon GP mechanisms run on the same data set, then if I give you the two outputs, then there are two epsilon, two delta differentially private. Okay, so it degrades, of course, because you reveal more, but you can still keep track of. Okay, and there are a much more advanced way of keeping track of that. This is the most simple kind of result. Okay, good, whoops. Okay, so we're gonna take that as a definition, and now we have to define what, in our case, is the mechanism, okay, in our setting, and how we can try to ensure such a definition. Let me quickly check the time, okay. Good. So maybe I'll show how we can enforce that, and then and then state exactly what property we mean. So the way we're going to change the algorithm, so we have this non-private algorithm that I defined before. Why is it non-private? We already know it doesn't satisfy this definition because the updates are not randomized, right? So if the output of the mechanism is not randomized, then it means if I change a bit the data set, in general, it will change the output with probability 1, and so this thing is not satisfied, okay? So you need randomness for this definition to hold. So what we're going to do is add randomness, which is classic way of ensuring differential privacy, which is sort of adding some noise with some appropriate scale to the quantities that leak potentially information about data. So in this case, it is the gradient, okay? When the user makes an update, instead of computing the updates as before, we just add some randomness on the gradient with respect to the local loss, which is the part that depends on the data. Okay, so let's say we add Laplace noise with some variance. Okay, and then you just do exactly as before. The algorithm stays the same. Instead of broadcasting the not noisy update, you broadcast that. Okay, and the algorithm is exactly as before up to that new noise addition. Okay, so this is our private algorithm now, and we can state the guarantee, which looks like this. So maybe the most important here is how we define the mechanism. So this is to reflect the assumption that I mentioned before, that the adversary is able to see everything that you're sending. So the mechanism for user I takes as input the dataset Si and releases the sequence of the updates made by the agent. Okay, so this is the output that we care about because that's what reveals potential information about the data. And we can show with this, okay, so with some sort of simple assumptions on the loss function, if we fix the number of times that a user wakes up or how many iterations each user does, and we sort of take some variance of the noise of the random perturbation to be inversely proportional to the size of the data set of the user, and some budget epsilon I that the user is free to set. Then we have that essentially if the initialization is independent of the data set, then for each user, the set of updates essentially they satisfy epsilon I bar 0 differential privacy, where this epsilon I bar is just t times the epsilon I. Okay, so the more iterations you do, the more information you reveal. So the budget sort of grows. Okay, so the more iterations you do, the worse the guarantee. Okay, we can do better than this by some advanced composition results, whatever. But maybe what's nice here is sort of like a sweet spot, which comes from this. Okay, so I'm assuming that some users in the network might have more data than others. And so people who have more data, they need to add less noise, which makes sense because they have more data. So when they compute a gradient, the information about individual data point is already averaged over more terms. So these guys are going to add not so much noise to their updates, and so they're going to make other people benefit a lot. While agents that have small data sets, they're going to add a lot of noise, so they're mostly going to send rubbish to other people. But because they don't put a lot of weight, we have this confidence in the objective that doesn't put too much weight on users that have small data. This noise is going to mainly be ignored. Okay, so it's kind of nice because in the end, the fact that users with less data are going to add a lot of noise is not going to ruin the accuracy that much. And we have some analysis for this. So what I just told you, you can see here. So essentially, this is the same thing as before, the sort of expected suboptimality gap after t iterations, but now for the private version of the algorithm with some noise. The first term is the same as before. So this will go to 0 very fast as the number of iteration increases. But now we have some additive error term that depends on the scale of the noise. And this one grows with the number of iterations, like I said. Okay, so there is a trade-off now. You have to, okay, sort of do enough iterations to reduce enough the optimization error, but not do too many that you have to add so much noise or reveal too much information. Okay, you can always compensate the fact that you do more updates by adding more noise to each update, but okay, then this term becomes big. Okay, so Now you cannot run the algorithm forever and converge to the, as close as possible to the optimal. You have to sort of, okay, so this is like the classic privacy utility trade-off that we expect with differential privacy. You cannot get it all, okay? And so like what I was saying before is that if for users that have small data sets, so small CI, even though their SI has to be big to protect their data, this is weighted by the CI, so in fact it's not, it doesn't penalize okay, the privacy loss or the loss due to privacy in the utility is not penalized that much by these users. Okay, so it is quite nice. Okay, you can even rearrange this expression and try to find the best way of scaling the noise across iterations and so on. I'm gonna skip that, but the main information is now the number of iterations rule the trade-off between optimization error and noise error. Okay? Good, let me check again. Okay, I have maybe a bit of time quickly to explain how we can maybe learn this graph. I'm going to be maybe quick so that I can show some experiments. So far I have assumed that this similarity weights between users were given, okay, which can happen in some applications. Maybe you have side information on the users, like maybe profiles or something like this, on which you could compute some similarity, maybe. But okay, it's not always the case, and it's not always reliable either. I mean, it's not clear how to get this similarity anyway. So it would be best if we could learn it, okay? So learn both the similarity, this collaboration graph, and the models. And so we propose a formulation to do that. So essentially by writing like a joint problem over the models and the graph weights W. So now we're learning the models, but also this vector of weights, which has size, okay, this is, sorry, some inconsistent notation. This should be n minus 1 over 2, okay? So there are as many possible weights as pairs of users. And we do exactly the same as before. So these were the two terms that I had in the original problem. But I need to add something else, okay? Maybe the obvious reason is that if I don't add anything, then if I minimize over W, I will always set them to 0, because this is what's going to minimize my objective function. And so if all the weights are 0, there's no collaboration, so it makes no sense. So I have to sort of regularize to force the weights to be non-trivial, not to generate to 0. And so one way we can do this, in fact, we have some flexibility in how we can set it, but one example of way which is nice, which is inspired from some graph signal processing approach, is this, to regularize the weights as follows. So you take minus the log of the degrees. Okay, so the degree vector here is just the sum for di is the sum of the wij over all j's. Okay, so it's the sum of the weight for a given user. This can be seen as a log barrier on the degrees. Okay, so if some degree goes to 0, that means a user becomes isolated. This goes to infinity or minus infinity, and so this objective function will go to infinity. So this will prevent this dumb solution of setting everything to 0. And so avoid that any user is isolated in the graph that we learn. And then we have this, which is a penalty on the weights, which allows us to control the graph sparsity. So people familiar with like sparsity-inducing regularization might be a little bit surprised that this is L2, because usually L2 doesn't yield any sparsity. And you're right. In fact, we already have some sparsity-inducing term here. So this term that we had from the beginning, if you think about it, is essentially a weighted L1 on W, okay? Because W is non-negative, so this is really like L1, but weighting the different coordinates differently. But still, so it's already giving some sparsity. So this is, in fact, to fight against the sparsity, to tune the sparsity. By having more L2 penalization, you will force the weights to be more spread out over different coordinates, so over different neighbors. And so you can make the graph less or more sparse by changing this beta, okay? And then what we do, we solve by alternating optimization, which is nice because we already know how to find the models given the graph. This is what I introduced before. We only need to now design an algorithm to update the graph given the models. Okay, and okay, I can quickly explain this maybe because it's kind of interesting maybe. So So now we want to update the weight, the graph. And so, of course, so far we were communicating along the edges of the graph, okay, which is now a little bit of a problem, because if I want to discover new people that are maybe similar to me but not right now connected to me, I need to be able to reach those users, okay? So what we're going to do to be able to communicate beyond the neighborhoods when we update the graph is by relying on an existing primitive which is implemented in distributed systems, which is peer sampling. So this allows you to, as an agent in the network, to request a small sample of random peers in the network. Okay, so this sounds like magic, and in fact it can be implemented in a fully decentralized manner. So we sort of don't reinvent the wheel and assume we have access to such peer sampling service. So at each iteration I can get a small uniform sample of you guys, and then maybe I can check whether you guys should become my new neighbors, something like that. Okay, so the algorithm goes very much like this. I didn't put the details here, but we initialize the weights. And then at each step, there is a random agent that wakes up, just as before. This agent is going to draw kappa agents with the peer sampling service. And if I do that, I'm going to ask you for your current model, your current value of your loss, and your current degree. And in fact, if you give me this, so it's not much, okay, it's just sharing your model, which we were already doing before. Sharing the value of your loss, this is a scalar, and your current degree, this is also a scalar. If you give me this, I have enough information to update the weight that I assign to you using a gradient descent step. Okay, so this information is enough. And then once I have updated this weight, I have to keep you informed that we have a new weight, because okay, this weight is symmetric, so it's shared. So I have to send back the updated weight. Okay, and by doing this, I make sure that we're always sort of making like some kind of descent in the objective function with respect to W. Okay. So we can show again of some kind of fast convergence rate here by some proximal coordinate gradient descent. There's some kind of interesting block structure, but I'm going to skip those details. And then this kappa number of users that I update the weights rules some kind of trade-off between communication cost and conversion speed. Okay, if I ask for a bigger sample, then I can converge faster, but it costs me more communication. And something that is quite interesting here that I want to emphasize is that, okay, we're still concerned about privacy, so what about the information that I can leak through this step? In fact, it's fine because we are only post-processing the models here. So this is one of the nice properties of differential privacy also, that if I give you the output of a differentially private algorithm, you can do whatever you want with it as long as you don't know the original data. This is going to keep, okay, this is going to remain differentially private. So here is the same, okay? We have already made the models differentially private in the first step. We're not touching the training data anymore in any of this step, so we are fine. We don't have to do anything more to maintain the privacy guarantees. Okay? I'll show some experiments to wrap up. So I'll start with some synthetic data to try to show a little bit how things behave in a controlled environment. So let's say we have 100 agents with a synthetic linear classification task. So essentially we have some data that we draw from some distribution that is user-specific. And then every user has some target model that we know because we generate the data. And the agent also receives, as a data set, a random number of samples, okay, drawn from that distribution and labeled by the prediction of the target model, plus some label noise that we add to make the task not too easy. So this is the training data of everybody. And then what we're going to do also in the first step is to cheat. So let's say we do have an oracle corroboration graph. So let's say we start with the simple scenario where we know the graph and it's given by the angle between the ground truth models that we know because we generate the distribution. Okay, so here we're sort of cheating, assuming that somebody tells us how everybody is related. Okay, and this is what you get when you use this oracle graph. So here I'm not learning the graph, only learning the models and adding that noise to guarantee privacy. This is what we get. Okay, so this is the test accuracy. This is the dimension of the data and of the model. The performance sort of goes down with the dimension because the number of data points remains constant. Okay, so the tasks become more and more difficult as the dimensionality grows. And essentially we get two extreme approaches. The top one, the blue one, is the non-private algorithm when I don't add any noise. So this is giving me very nice test accuracy. So this is on average over the agents. And then the bottom one is the purely local models. So this is the other extreme where I don't share anything and I just learn based on my data. So this is not very good. Okay, and what we see is really what we hope to have with a sort of differentially private algorithm is to do in between, okay? By having some budget, so smaller epsilon is more privacy constraints, I can achieve sort of something in between the two, okay? So do significantly better than not sharing anything, but with still some strong guarantee that I'm not revealing much about my individual training points. So this is nice, and we can see that, okay, the gains are more strong for the users that had little data, so there is some kind of like wealth inequality kind of fixing here, where of course if you had a lot of data, maybe you don't get so much from this procedure, but you certainly get as good as what you would have learning on your own, but for users that have small data, then those get a very big boost. Okay, and now we can look at what happens when we don't know the graph and we learn it. So this is where we have designed the task so that we have a cluster structure with like 4 clusters of different size, one of them very small, one of them very big. And here we learn it with the procedure that I mentioned, okay? So we learn both the models and the graph. And what we get is something like this, where we do recover essentially those 4 clusters of different size. This is the W matrix, okay? So of course we have only finite data samples, so we miss some of the similarities, but we are still able to sort of approximately recover this structure, even though it's like very unbalanced clusters and things like this, which are typically not so easy to recover. And if you were doing some classic heuristic like KNN graph over the model parameters, you would not be able to get that structure. Okay, so we're really sort of being able to adapt to the ground truth. And of course, if you have more training data, you will get closer to that. Okay, and then this is on real data. So those are data sets that are where data is collected at the user level. So we have some activity recognition on smartphone sensors, some vehicle sensor, some people rating computers, and some results in schools, whatever. So all those data sets sort of have a natural user kind of dimension that we can use to split the data among different nodes. And okay, what happens is that typically, so this is for linear models. This is learning a global model for everybody. We know how to do that with decentralized algorithm. This is learning a purely local model for everybody, okay? This we know how to do. And what we show is that essentially we do a lot better with our approach, okay? So all those data sets, all the users are different enough in their task that the global model doesn't work that well. But of course, it's, with our approach, we can share information instead of learning on our own, and overall we do better, okay? And we also have some approach to learn nonlinear ensembles, sort of like AdaBoost style kind of algorithm in decentralized way. And okay, so we can also learn nonlinear models and compare to the global and local versions, and okay, it's the same, okay? So our method really allows to, in settings where users have different tasks, to outperform those two extreme strategies of learning the same model for everybody or learning a model in isolation. That's it, and maybe okay, I can say a few words on the ongoing and future work. So some extension to non-convex setting. So you can define the algorithm in the same way for non-convex, but the analysis, okay, has to be updated. I think there are okay, a number of modeling things that can be changed also for non-convex problems. So in particular here, we sort of smooth the models, okay? If two users are similar, we want their models to have similar parameter. In fact, we would probably rather smooth predictions, okay? If you think about it, what you care is more that the models make similar predictions, even though maybe they have different parameters. When you get to very complex models, having same parameters is sort of, okay, you can have very different parameters and still make similar predictions. So it would make a lot more sense to smooth predictions, but same, so it makes the optimization problem quite a lot more complicated. But this is probably a good option for non-convex models where you would lose convexity anyway. This is more like a statistical learning theory kind of thing that we would like to make more clear what kind of assumptions between the data distributions and what kind of weights we can estimate to prove some generalization guarantees. Study the dynamic setting, so we have a PhD student starting on this, so which I think makes a lot of sense, so where the data arrives sequentially. So at the beginning you have very few data points, so you don't know who is similar to who, but as you get more data, you can expect to converge to the ground truth kind of similarities and so on. Okay, and something that I'm also very interested in is something closer to like privacy and maybe the intersection with things in crypto, which is how to reduce the noise that you need to add to satisfy GP. So there are ways to sort of combine differential privacy with some secure aggregation primitives, for instance, so that instead of sending you my model, we run some secure aggregation procedure that only reveals the aggregated model, which is the only thing that I need in the end in my algorithm. And this allows you to add less noise because you don't observe the individual models, but only the aggregated version. And okay, some robustness also to malicious parties. So here I'm assuming everybody is honest, so it's following the protocol, okay? Everybody's curious. So it wants to learn about your data, but it doesn't do anything bad, okay? It follows the protocol, it responds, and it sends what it's supposed to be sending, and so on. In many practical scenarios, you might have some malicious parties, so parties that would maybe try to influence the output of the protocol and things like this. So we have some a bit of work in that direction, but this is a hard setting. That's it. Thanks a lot.
Thank you very much. So, questions?
Yeah, so thank you for the very nice talk. I have one question related to the place where you add the noise. I mean, you were adding the noise after the gradient.
Yes.
Is there a specific reason for that? I mean, intuitively, I would prefer to add the noise to the data and then compute the gradient instead of adding the noise to the gradient, even though I'm exchanging the gradients. But
right. So this is something you can do, but this is usually not a very good idea. So it depends also on the definition that you take for differential privacy. But the good thing about adding it to the gradient is that we can leverage some properties of the loss function that already make the gradient not so strongly dependent to individual data points. So if I take the logistic loss, for instance, no matter the representation space of the data, I know that the loss is sort of between 0 and 1, for instance. And so this helps me a lot in scaling this noise, in not making it depend too much on, let's say, the boundedness of the domain of the data or something like this. So it is usually quite profitable to add the noise. I mean, if it is the gradient that you're going to use, typically it scales much better to add the noise to the gradient because you can better quantify how much noise you need on this. Another possibility is to take the data and try to make that data differentially private, sort of like the local model of differential privacy, for instance, where you take a data point and you perturb it, and then it's free, like you can share it publicly, and everybody can do whatever they want on this. This is sort of protected. This protects for a much bigger, this is a lot more conservative because it protects against everything that you could do about this data. So here I'm only protecting, in a way, the gradient, what the algorithm needs.
Yeah, but my idea was to adding this to the data, but then compute a differential privacy over the gradient, not.
Okay.
So I just wonder whether you think that there will be any advantage or not doing that. I mean, it was more a curiosity.
Yeah, okay. So that's an interesting question. I think okay, it will depend a lot on the loss. So I'm not so sure you can easily bound the sort of sensitivity that you need to bound to scale that noise nicely. But okay, yeah, it's an interesting question whether you could still keep the same protection for the gradient but adding the noise to the data.
Thank you. Yeah.
There are results on sort of private convex optimization and things like this for machine learning that tend to show optimality of this, though, adding to the gradient for some classes of problems.
Hello. I've got a question about your eta I, your noise. Is it once and for all you generate it, or is it at each iteration?
No, it needs to be different at each iteration. Yes, because otherwise you can cancel it or. Yeah. So this thing is drawn. It should be an ni of t. In fact, yeah. The notation is not that nice.
Hello, great talk, thank you. I was wondering, since the graph, the correlative graph is made from similarity between users, isn't it by design not privacy preserving? I mean that users could, knowing their neighbors could, with side information.
Yeah. So that's a good point. Maybe that's also why we were interested in learning it, because the way I presented things here is I'm learning those similarities from differentially private models, so I'm fine. If I define the similarities in another way based on the data, yes, you have the potential danger that it violates differential privacy if it depends on the data. So in this case, you might have to also add noise to these similarities to make sure that they don't reveal information. In some use cases, this might appear as a trick because there might be some correlations or whatever, but if you have some held out profile on a user that is different from the training data, and you make the hypothesis that this is independent from the data, okay, but this starts being a little bit fishy, right? Because, so yeah, this is why we're kind of happy of maybe learning it based on the differentially private models.
Okay, I don't know if there's any other questions, but I have one. So you say that you have a compromise between level of noise and accuracy. What is the number of iteration?
Mm-hmm.
Because I don't know if you can show again the slides in 24. Or, I don't know.
Yeah, no, it's this one, right?
Yeah. Okay. 21. Okay. So my question is, and you show that also in your results. Okay.
Yeah.
So my question is, how much the algorithm, the descent algorithm, has an impact on your result at the end? I mean, because you need to leverage this number of iteration. Okay. If you are correcting too much, okay, and you are adding too much noise. Okay. So there is this trade-off. Okay. So I mean, from what we have seen this morning also with different kind of algorithms that Francis presented, I mean, is there an impact? Can I choose my descent algorithm also knowing that I want this privacy? Yes.
So that's a very good point. I think maybe one of the points that Francis made, that you should decentralize the fastest algorithm, is also somewhat true for this, because the less iterations you need to do, okay, the less you have to split your privacy budget among a lot of things, right? But there is a subtlety here, is that different algorithms might not compute the same information from the data, and so if your faster algorithm depends more on the data, like maybe does several steps of gradient descent locally and things like this, then it might not be so clear. So I think in our setting, the best strategy is to decentralize. So this is in decentralized scenario. There are privacy-preserving optimization algorithm for the centralized scenario. Some of those are known to be optimal, so I think we should be decentralizing those in a way. But yeah, this is a very good question.
Yeah. So the next question is, I mean, depending on my loss function and the task at end I'm solving, I mean, so sum of losses, or I mean some specific difficulty of the link to my task, I might have to change.
Yes. So here we're also using very simple this Laplace mechanism. So there are other ways also to enforce differential privacy. And if you are in a very high dimensional space, for instance, you might be better off using, let's say, greedy algorithm, because greedy algorithm would reveal very little about, each iteration will reveal very little and something independent from the dimension. And so if the solution is very sparse, for instance, this might be a much better way to go. So yes, so there is a lot of, so the AdaBoost sort of algorithm that we present is one such algorithm, so where you can only perturb something that depends on a single, I mean, very loosely depend on the data, so you need maybe more iterations, but each thing is, okay, carries very little information, in fact, and so you can use different strategies to randomize. So yeah, there's a whole space of combinations, which I think is not very well explored at the moment. People have focused in differential probability, at least on, okay, mostly on the mainline algorithm like gradient descent and SGD in particular. So SGD is a very interesting case also because you subsample. So if I compute my update on a subsample mini batch, but I don't reveal the mini batch to you, you can show some privacy amplification, for instance, by doing this. So the randomness of the sample that you don't know contributes to improving so there's a lot of those things that I think are very interesting to study and combine because,
So, is there any other questions? I don't think so. So now we are going to thank you again, Aurélien.